Geometry lesson 46. This in your book is on page 301. We're talking about triangle similarity. You'll notice that it uses a lot of the same letters in terms of acronyms as triangle congruence. So let's kind of go over the similarities and differences. Congruence, what does that mean in terms of triangle congruence? Triangle. Same size and shape, right? Yep. Same size and shape. All right, what's the difference between congruence and similarity?
Similarity, the angles are same.
They have that in common. In when two triangles are congruent and when two triangles are similar, the corresponding angles are going to be the same. They're going to be congruent. All right, what are the differences between two triangles that are similar versus two triangles that are congruent to each other? Not the same size, precisely. All right, so whenever two triangles are similar, the corresponding sides are proportional, but not necessarily congruent. All congruent triangles are similar, not all similar triangles are congruent. Does that make sense? Okay, so you could think of it as a dilation, meaning that we're changing the size. We're either making it bigger or smaller than whatever the original is. Okay, so two triangles are similar if all their corresponding angles are congruent. Since the sum of any triangle's angles is 180 degrees, we only are required to have two angles be congruent to prove that the triangles are similar. Okay, and I think that we've talked about this, but let's just go ahead and reiterate this. How many degrees are in a triangle?
360.
Okay, good. All right. Michael Pipes said 360 degrees. Make sure this is recorded. But then he said he was just kidding. It was 180. So we're not really sure if he was kidding or not. We're going to assume that he wasn't. All right, and he just caught himself. All right, there's 180 degrees. So if I know that there's a 30 and a 60, I know 90 degrees are spoken for, so I know that the remaining number of degrees on that third angle has to be 90. Right? So if I had 30 and 60 in one and 30 and 60 in the other, both of them have to have a remaining 90. Therefore, they have to have that third angle congruent. And that's what we call the third angle theorem, and we've already seen that show up on test questions, right? The third angle theorem. If two angles of one triangle are congruent to two angles of another triangle, then their third angle is congruent. That's what the third angle theorem means. So does that make sense? We remember these things. Right? The reason I reiterate this stuff that you've heard over and over again is because when we get to the test, do we have a tendency to forget stuff? All right, so memory is based upon, and unfortunately, it's based upon repetition. The more that you repeat the information, the better chance that you have of being able to recall it. And math, just like anywhere else, is about recall, right? Because when you get to that test, what you can't recall, you can't use, right? So it's like looking in a toolbox and not being able to find what it is that you need to find. It might be in there somewhere, but if you can't find it, it's useless to you. All right, so postulate 21 is angle-angle triangle similarity postulate. We don't have to have side congruencies in order to prove that two triangles are similar, right, like we do with congruence. In congruence, we have to have a side congruent to a side at the very least. 845. Yep. Okay. In triangle congruence, we have to have at least one side. We could have two, we could have three, but we have to have at least one. Now, in similarity, I don't have to have a side, right? Because we're not trying to prove that two sides are congruent. All we need is proportions. So that's what we'll see with the SSS and the SAS is proportions, not congruence. But at the very least, angle. So if I've got a proof that's saying prove that these two triangles are similar, the quickest way to get there, if I have whatever given information I have, is to say, well, these two angles are congruent to these two angles. That's enough. I can stop right there. So doing triangle proofs, to me, is all about the quickest way to get there. Right? So this stuff is really important being able to recall. So if two angles of one triangle are congruent to two angles of another triangle, then those triangles are similar. Again, you have to be able to split and understand the difference between congruence and similarity. Do we understand the differences between those two things? Okay? So we want to be able to understand the difference. What does that symbol mean? congruent, what does this symbol mean? Similar. Okay? So if I show you this, all I'm trying to prove is that they have corresponding angles congruent, corresponding sides are proportional. Okay? If I'm over here on the left, right, I have to have corresponding angles congruent, and I have to have corresponding sides congruent. All right, let's move on. Okay? It's not always necessary to know a triangle's angle measure to determine similarity. Another way to determine similarity is to verify that the lengths of all the corresponding sides of both triangles are related in the same ratio. That's just their way of saying if I can prove that all three sides of a triangle are proportional to the other three sides of another triangle, that's enough. I don't even have to have angle information. So the reason we go through all this stuff is because my given information is going to be different from situation to situation. It might be the same from one to another, but we need to be able to solve questions given different types of information. Okay? Because you're not always given the same information. You're not always given it in the same way. Okay? So when we talk about proofs, proofs are all about logic, right? And being able to get from this step to this step to this step. And it really is about the tools that exist in your toolbox. So the more of this stuff that you know and understand, the less frustrating proofs actually are. And I'll admit, proofs are probably the most frustrating thing in math, right? I would say probably most of you would nod your head up and down. I hate proofs, don't like proofs, right? It's a lot of work, right? I have to know a lot of stuff, and it can get really frustrating. The more that you know, the less frustrating it actually is. And I say that not because I like proofs, but over my years of teaching this subject and other math subjects, I have found that proofs have gotten easier. And it's not because I've memorized the steps, it's because I understand the math better and better and better. All right? So the better that you understand it, the easier. I'm telling you, the easier it will be. So don't just blow this stuff off. Don't not take notes, because if you want proofs to continue being hard, keep doing what you're doing, right? Don't take the information in, right? Just listen. Don't take notes, and I'll guarantee you this, proofs will continue to be really, really hard, okay? So if the lengths of the sides of a triangle are proportional to the lengths of the sides of another triangle, then those triangles are similar. All right, then we've got one more, which is side angle side, which we use for congruence. Here we can use it, but notice that, again, the side portion that we're looking at is not congruent, but proportional. So one final way to prove similarity is the side angle side similarity theorem. You'll notice that it's similar to the congruent postulate that you've learned about, except if two sides of one triangle are proportional to two sides of another triangle and the included angle is congruent, okay? Two sides proportional, included angle congruent, then the triangles are similar, okay? Does this make sense? Feel like we understand some of this? Okay, I think that's might be the last slide there. Okay, so let's see if we can take a look at question here. All right, here's a real world situation where they're using similarity. Now, as dull as some of this stuff is, it actually does have a real world use, because sometimes we want to measure things that are immeasurable in terms of convenience, right? Here, what they're trying to do is they're trying to measure the approximate, oh gosh, I can't draw on this again, right? Okay, they're trying to measure the approximate distance or the width of a river, right? Well, let's say we're trying to measure the length across a certain area of the Mississippi River. Do you want to swim across the Mississippi River with a rope tied to you? Do you want to get in a boat and try to go across the Mississippi River? Probably not, right? That's inconvenient, but we can figure it out by using similar triangles. So imagine that we are at point X, and on the other side of the river, make it the Mississippi, make it something really wide, there's a rock. There's a landmark that we can eyeball, right? Does that make sense? Okay? Now, I'm on my side of the river, and I'm at a section that's relatively straight. It's parallel with the river, right? What I can do is I can start walking, and I walk about 20 feet, okay? And I've got somebody else with me, and we plant a flag, okay, at that spot, right? So we plant a flag there, right? I keep going. I plant another flag about 10 feet further on, and then I turn away from the river and I walk 30 feet and we plant another flag. And what I see is I want to plant that last flag where you see Sally at a point where I can see that first flag that I planted is directly in line with the rock that's across the river. And what I've created is two right triangles. Okay, do we see those? Okay, now if I look at this, what do we know about vertical angles? Vertical angles are what? Congruent. So if you look at this angle created here at where we see John, right? We have two intersecting lines that are going to form vertical angles, correct? Okay, good. All right. So what I know about this is that I've got an angle there, okay? I've got a right triangle, two right triangles, correct? Okay. So I know that those acute angles are going to be congruent. So we've got two right triangles, we've got an acute angle, okay? And we have legs that are proportional, correct? I mean 10 to 20, right? Here, let me come back and so we can actually draw this here a little bit. Let me find. Okay, so let's see. Here's my rock. Okay. Here's my river. Okay. Here's flag number 1. Here's flag number 2. Here's flag number 3. Here's flag number 4. Okay. Okay, and what I am looking for is the length of this red line. Now, I know that this is a right angle. I know that that's a right angle. Let's see, this was 20. This is 10. This is 30. So, corresponding sides should be proportional. Okay, these two triangles should be similar. Okay? If nothing else, because what I said is that these two angles are congruent, which means don't we have angle-angle similarity? Okay, so we know that they're similar, which means their corresponding sides are proportional. So can I write a proportion to solve for x? Okay, somebody besides Michael help me with that proportion. Okay, so you're doing 20 over 10. All right, I see you working there. And then what?
30 over x.
X over 30. It can't be or, right? All right, it's got to be that way. If I'm going to do 20 over 10, meaning I'm doing big triangle over a corresponding side of my little triangle, then I have to do big triangle x over corresponding side 30, right? He's absolutely right. All right, so let's solve from here. Maddie, help me out. What are you going to do to solve for x? 30 times 20, what is that? What's 3 times 2? 6. What's 10 times 10? 10 times 10. Right? What is it? All right, so we should be 600, right? All right, so 600 equals 10x. What are we going to do here? Divide by 10. Okay, so I should be able to, cross out. What do I get? 60 equals x. So at this particular point of the river, if my unit is in feet, right, so the river is 60 feet across. So do we see how we can use this to solve real-world problems where it might be inconvenient to try to, run a tape measure, right? What's the average length of your tape measure? 25 feet? 25 to 35. Everything that we ran here, though, right, We could run a 20-foot line and plant a flag. We could certainly do 10, and we can probably do 30, right, and keep it fairly straight. All right, but am I going to be able to run a line 60 feet across a river? No. All right, what other real-world situations might be inconvenient to try to measure? If we were trying, things that we might legitimately need to know the length or distance of, that might be really, really hard to run a tape measure for. A school building? Sure, think bigger. A mountain? Yeah. A tower? Yeah. A mountain. I heard mountain. I heard tower. An airport. Okay. Moving distances, like the distance between a plane and an airport, right? How about the distances between stars, right? I mean, if similarity is similar, all we're talking about is proportion. So can I use a really small triangle and solve the proportion to find two distances that are very far apart, so long as I can prove that the triangles are similar? Absolutely. So we use trigonometry, triangles, the study of triangles, to find things that would normally be immeasurable by human basic means. Does that make sense? Right? So if I was going to have you write a paragraph over this lesson, right, this is a really easy one to do that on. All right. Let's see, do we want to look at one more of these, or do you want to do a problem from your homework? One more from here. Let's see. This says explain why these are similar. What you want to keep in mind is that sometimes what we need to do, right, it says triangle ABC. Okay, this is triangle A. I can't do it. All right, triangle ABC is the big triangle, right? We want to prove that it's similar to triangle DBE. That's the little triangle. Sometimes what we need to do is actually separate the two triangles from each other. I want you to imagine DBE is just overlapping, right? It's laying on top of the big triangle. Okay, so it's not like I have a triangle and I have a trapezoid. Okay, they're not next to each other. One's over the top of the other. So they're going to share angle B, correct? Right, they're going to share angle B. They both A, B, C, D, B, E. All right, so because they share angle B, is angle B equal to angle B? This is like a no duh type of thing, yeah? We call that the reflexive property of congruence. Does that make sense? We do that a lot in Algebra 3. Something is equal to itself. Okay, so are those two triangles similar? Yes. Yes, they are. And even then, we could have done angle D to angle A, okay, because corresponding angles are congruent, all right? All right, so they want you to find BC, so we would be setting up proportions to do that. I'm going to move on. Do we want to, we have several different proofs in here. Is there a chance that one of these proofs could show up on a test question? No, probably not. All right. Yeah, there is. Just because we didn't go over it doesn't mean it won't show up on a test, which means you might want to be able to come back here, look at the answer key list, or ask a question. Okay? But because we're short on time today, I do want to answer a question from your homework. Number 6. Well, we're not dealing with right triangles, so we can't use right triangle congruency. Because one, we're not trying to prove that they're congruent, we're trying to prove that they're similar. 2, they're not right triangles, so no, I can't use like. Okay? So you've got to use proportions there. Remember here also, angle C is congruent to angle C. Right? Okay. All right, let's look at something that's actually in your homework, though. Let's see, what questions did I give you? 8 through 13. Okay. Looks like question number 8. Question number 8. Let's take a look at that. Okay. Question number 8 reads like this. It says a gardener wants all the triangular gardens in a yard to be similar shapes. garden has sides of 3, 4, and 6 feet long, if the second garden has to have sides of 12 and 16 feet corresponding to the 3 and the 4-foot sides of the outer garden, what is the length of the third side? All right, so what's the length of the first garden in sides? 3, 4, 6. Right? And this other one, we want it to be similar. What's corresponding to the 3 in the second one? 12. What's corresponding to the 4 in the second one? 16. All right, what is the similarity ratio here? What am I doing to 3 to get 12 and doing to 4 to get 16? Multiplying by 4. So what am I going to do to 6? So what should I get? All right, was that easier than what we might have made it? Just left to ourselves. 24 feet is pretty easy. All right, you said it was 8 through what? 8 through 13, and then what? 2 through...
17 through.
Okay, so let's look at question 20 then. All right, 20 is a 46. Right? Question number 20. A house has a triangular roof structures or gables, which are similar to the gables of the attached garage. If the base of the house gable is 25 feet and the base of the garage gable is 40 feet, what is the similarity ratio of the two lengths? All right, so 20. Basically, all you have to do here is simplify 25 to 40. Right? What can I divide both those by? 5. So what's 25 divided by 5? 5. And what's 40 divided by 5? 8. So the similarity ratio is 5/8. And this is handy. You know, I know as much as I give you guys a hard time on the essay questions about not using construction, but can I use construction here to create something that's going to look similar but not the same shape? So if I've already made my garage and I want it to have the same general shape, right, I'm going to up everything or reduce everything by the same amount, right? So I'm going to go 5/8 of whatever I've got over here. Does that make sense? Okay, so, you know, I'll say this for guys that are in construction, they make good money for doing what they do. If you go to build a house, most of your cost for your house is not the materials. What is it? It's the labor, right? And why is the labor so expensive? What's that? Well, yeah, but that's what I'm talking about on the labor. You pay those guys by the hour, right? Why is their time so valuable? Because of what they know. And I guarantee you a lot of what they know is what? It's geometry. They know their geometry. And you know what they know? They know similarity ratios, right? So let me say this. I believe this. I think what you guys learn in this class is as valuable or more valuable than a lot of stuff that you learn. All right? So don't blow it off. Okay? Because you don't know what it is that you're going to end up doing in life. Okay? And this what you're getting right now is free, but could be worth many, many thousands of dollars to you. Right? Okay. So I'm going to close it up there. Hopefully we've learned something today, and we've learned enough to be able to do our homework, be successful at it.